As we have seen the difference between distance and displacement, and also have a small idea about the difference between a scalar and a vector, we can go forward and look at a few graphs that are there. The basic or the simplest one is the distance time graph. So the y-axis is always written in terms of either distance or displacement. The unit is in terms of meter. The x-axis in terms of time. The unit is in terms of seconds. Now, depending on the type of graph that is drawn here, we can arrive at different conclusions that are there. So the first thing is, let's see if we have a curve which looks like this. So it starts from the origin and it is having a 45-degree angle. That means in between the displacement and the time axis, or the distance and the time axis, we have this line that is drawn. So this graph is called as the displacement time graph. In this, let us say we have marked time as 1 second, displacement as 1 meter, again 2, 3, 4, and here also 2, 3, 4. Now, if we go ahead and draw, let's say, some dotted lines onto the x and the y axis, that is dropping perpendiculars, we can see that our values that are there are almost the same. So for instance, let me just get this right. So this is our x-axis that was there. From 3, I can drop a perpendicular. So from 4 again, I can drop a perpendicular. So this is going to be 2 second, this is 3, this is 4. Okay, so you can see that with increase in time, the displacement is also increasing. So this graph that is there is an indication that the motion of the body is uniform. So we will look at the graph that is there here, and based on the graph we can talk about what type of motion it has. Now, an important factor that we can arrive at from the displacement time graph is velocity. So we know that velocity is nothing but displacement by time. The symbol for velocity, since it is a vector, we will write it as v vector is equal to s vector by t. Now, let us find out how we get velocity from this graph. So for this, what we do is, we will take the slope that is there. So when we tell slope, what we are going to do is, we will take a small triangle. And I will name this as A, B, and C. So if I write slope, it is nothing but taken as AB by BC, or mathematically this triangle that is generated here is nothing but tan of the angle. So if this angle is theta, then this angle is also theta. So tan theta is AB by BC. Now let us look at substituting in this. So the slope is given as AB by BC. So we can take, let's say, AB is nothing but 3 minus 2. And BC is again 3 minus 2. So I will get this as 1 by 1, which is nothing but 1 meter per second, which is our velocity. So from this graph, I can tell that the velocity is 1 meter per second. That means it is increasing uniformly. The velocity is 1 meter per second as displacement and time increases. So that we can see in between 1 and 2 also, if we measure, we will get 1 meter per second. The same between 3 and 4. So from the displacement time graph, the most important quantity that we obtain is velocity. So what are the inferences that we can draw from the distance time graph? So if I draw this as my distance time graph, and let's say I draw two curves that are there. Now in geometry, even a straight line is called as a curve because it has an equation by which we can draw it. So this is displacement, the unit is in terms of meters, time in terms of seconds. So I have two curves here, A and B. And as we can see, both of them are going to have different slopes. So if I construct the triangle here for A, and if I construct the triangle for B, it is going to be two different slopes. So let's see. So this is one. The same thing when I do it for B, the slope, you can see that the triangle that is generated is much smaller. You can draw it bigger. So what I've done is for A, whatever it was, the same reference point I've taken for B also. So what do we understand from this type of a graph? The understanding that we arrive at is greater the slope, greater the velocity. So if we have a larger slope, that means the velocity is also equally larger. Now we can also have graphs which look like this sometimes. So a graph like this. Again, this is a valid graph because displacement is a vector. So we can have both positive and negative values. So the positive negative sign would basically depict the direction that is there. Now here if you see, the angle that is measured is greater than 90 degrees. So theta I will take. Theta is greater than 90 degrees. So what is the meaning of this? Now here if you see, the slope that is there is a negative slope. The slope that we get here is a negative slope. That means the object is returning to its reference point. So from where it had started, it is returning there. That is the understanding that we get. Sometimes when we see our graphs look like this also. So these are some real life cases where we can apply this and we do find it like this. Let's say something which starts off something like this. Now when we look at this, what is it that we can glean from here, or what is our understanding that is there? So again, this is displacement in terms of meters, time in terms of seconds. So any graph that is there, it is imperative or important that we draw the axis and we label them. So here if you can see, I can go ahead and let's say draw lines wherever these points stop. And you can see that they form different figures. Now the reason why I am drawing the horizontal line also is, you can see that these are made up of different regular geometric figures that are there. So a series of stacks of rectangles and triangles together, we can actually determine a couple of other things also from this graph. So here the slope that is there, in any case, the velocity is going to change. So if I see, the first one will have a positive velocity slope, positive slope, the third one also. So if I label this as, let's say 1, 2, 3, 4, 5, and this has 6 segments. So there will be, the fourth one will also be positive, but we've already seen that when it is having let's say a slope or an angle greater than 90 degree, that is with respect to the time axis, the slope is going to be negative. So I have written positive slope. I get 4 positive slopes here and negative slopes are 2. So what is the meaning? That after some time, the object again comes to rest. So if this is 0, starts from rest, and you can see that the velocity is varying, or the velocity is changing. And this change need not be uniform. So the time difference that is there. So here you can see that the time difference is much larger. Just by looking at it, you can tell, compared to the first or the sixth segment. The sixth segment has the smallest time, whereas the fourth segment has the largest time that the body has been traveling. So the inference here is that since there are multiple lines, there are multiple slopes, hence the velocity is changing. Now we can take another graph which looks like this. So we can have multiple, let's say, displacement time graphs. So we can have a graph which looks like this. So here you can see that there is no cuts like in the previous one. Again, this is also a graph where we can tell that what we see here is that velocity is changing. That means if I take the slope here and if I take the slope here compared to the slope here, it's going to be different. So here also the velocity is changing, but the change is continuous. So the velocity is changing continuously. So this is the understanding that we get. So from the displacement time graph that is there. So now we have seen displacement time graph. Let us move ahead and have a look at the next set of graphs that are there, which has velocity and time that is given. So these graphs are called as VT graphs. Again, velocity is meter per second and time is in the form of seconds. Now, when you look at a velocity time graph, there are a couple of things that you can determine or understand, beginning with the way the graph is drawn. So let us say we have something like this. So here you can notice that I have not started from 0 but at some constant value. So the meaning of that is the body already at initial time equal to 0 had some velocity, and this velocity we call as the initial velocity u. And wherever our graph ends, that will be the point where we will call it as the final velocity. So this is the final velocity that is there at, let's say, some time t. So at time is equal to 0 seconds, u is the initial velocity. At time is equal to t seconds, v is the final velocity. Now, from the velocity time graph, what can we estimate? We can do two things. The first thing is we can go ahead and find the slope. Now the slope in this case is going to be nothing but equal to, if I take it as, let's say, AB by BC, that means we'll have to draw the triangle. So we can take, let's say, this triangle itself. Since I already have U and V that is marked, I will take this triangle. I'll mark this as A, B, and this point as C. So I have my initial velocity U that is there here, 0 meter per second. Now if I look at AB, AB is nothing but V minus U, final minus initial velocity, divided by BC is nothing but T minus 0, which we get it as V minus U by T, or this can be written as delta V by T, which is nothing but acceleration. So from this graph, we can determine what is the acceleration by looking at the rate of change of velocity with respect to time that is there. So this, I can rewrite this as delta t because this was t minus 0. Now for instance, instead of 0, if the graph was somewhere further in front, then we would have to take it as t2 minus t1. So that is nothing but delta t. So the rate of change of velocity is acceleration. The slope gives us the acceleration that is there. Now let us have a look at what else we can find. Now it is a well-known fact that velocity is nothing but displacement by time. So if I have to find out what is the displacement, what will I do? Velocity into time. Now this is from the formula. So let us have a look by drawing a graph. So I'm trying to consider the similar graph that we have already done. So I have this to be velocity, meter per second. This is time in terms of seconds, 0. This point I had it as u. Let's say this point is v. And we saw that this point is nothing but time t. Now what I will do is, I will draw a line that is there here from u onto this dotted line, and from this blue, if I draw it here, it can be seen that I have two regular geometrical structures here. One is a triangle, the other is a rectangle. So since this is already 0, we will label it as O, the origin. This point, let's say OU is there, so we'll remove U here. O, A, B, C, and this point as D. So here at A, I have my initial velocity. That is triangle ABC and let's say plus rectangle ACDO. Now what is it that we are trying to obtain from this graph? Velocity into time. And if I have to do velocity into time, I am basically trying to obtain the area under this curve that is there. Because the moment I do velocity into time, I am looking at the area. And you are multiplying both the axes. No? So this will be the velocity axis, this is the time axis multiplied. Now in general, we have to look at the quadrilateral OABD. So what I have done in order to make things a little more easier and more understandable, I have taken triangle and rectangle. So the area under the curve would give us the displacement that is there. So from a VT graph, two things can be obtained. From the slope, we can obtain acceleration. Also from the area below the curve that is there, we can obtain displacement of the object. So let us see if we do indeed obtain displacement. So what we can do, we have got two objects, right? Triangle and rectangle. So let us take the area. Area of, let's say, triangle ABC will be nothing but half base, that is AC, into height, which is BC. And area of the rectangle will be nothing but side into side, right? Length into breadth. So it can be taken as, let's say, AO into OD. So let us substitute. Now, AC will be nothing but T minus 0, which is similar to OD. So I've got half into T minus 0. BC is V minus U. Plus AO is nothing but U minus 0. And OD is as similar to AC, which is nothing but T minus 0. So I will get this as half. T minus 0 is T, V minus U plus U into T. So you can see here from this graph, what are we getting? Here there's no sign of displacement. So what we'll do, we'll take time common. So my expression was half V minus U into T plus UT So if I take t common from here, I will have v by 2 minus u by 2 plus u, which is nothing but t into v by 2 plus u by 2, which is t times v plus u by 2. So v plus u by 2 is the average velocity that is there. So I will have t into delta v. Now since I took it as the origin was 0, I would have to get t2 minus t1. So in our case it was t minus 0. So we can simply write this as delta t into delta v. And this would give us the displacement that is there. So hence the slope of the vt graph would give us acceleration. At the same time, area under the curve of a vt graph would give us the displacement that is there. Now we have finished displacement time graph, velocity time graph. Now the next graph that is there is the acceleration time graph. So before we get to the acceleration time graph, let's see the different types of velocity time graph that is there. Now we have already seen this graph where we can tell that if I have velocity meter per second and let's say time, which is in terms of seconds, this is nothing but an object moving with uniform velocity. So I'll just put an object here. Yes, an object moving with uniform velocity. But if I draw a graph which looks like this, now here what is happening, I have not labeled the axis, we'll go ahead and do it. Time is in terms of seconds, velocity in terms of meter per second. So you can see as time increases, the velocity is constant. So in this case, the object that is there is moving with constant velocity. Now, depending on the slope also that is there, if greater the slope, then we get a greater acceleration that is there. There is nothing to talk about, let's say, displacement when we are looking at different slopes that are there. Whatever is the area under this curve, that would give rise to the displacement. So if I take the blue line that is there, so if I drop a perpendicular from here to here, the area under the blue curve is different from the area under the white curve, even though both are triangles. In the sense, so if I take this as, let's say, A, B and C, and this, let's say, is DEC, both are triangles. So triangle ABC, triangle DEC would have different slopes. So the slope of ABC would be much greater than the slope of triangle, let's say, DCE. Therefore, the acceleration would be higher. So similarly, you can see the area that is covered. DCE has a larger area compared to ABC. So accordingly, displacement also can be calculated. So what if we have a curve that is continuous, just like how we saw in displacement time graph? If I have a curve which looks like this, in the velocity time graph, so this is meter per second, this is time in second. So if I have a graph which is drawn like this, that means velocity is changing continuously. The graphs are labeled separately, the axes are different, but then the understanding is one and the same that is there. Now let us move on to the next one, which is called as the acceleration time graph. So the y-axis is in terms of acceleration, meter per second square. The y-axis is in terms of second. Now we always make sure that the x-axis is written in terms of seconds because it is easier to measure time along the x-axis. And let's say displacement, velocity, acceleration, anything that is varying with respect to time, we put it on the y-axis. Now this is a standard procedure that is there. Anytime we try to measure something with respect to time, the time remains on the x-axis, whereas the quantity that we are measuring would come onto the y-axis. So we'll go ahead and let's say draw something like this. That means for any given instant of time, the acceleration that is there is going to be a constant. So as time is increasing, the acceleration remains the same. So A is constant with respect to time. Now, we cannot find the slope of this or any curve with respect to acceleration time graph because there is no physical quantity which will describe the slope of acceleration with time. So for instance, we can say that we are accelerating. So if you look at your vehicles, either a two-wheeler or a four-wheeler, the maximum that you can do is you can accelerate it. You cannot go beyond acceleration. So therefore, there is no slope for this graph, but we can find the area. Now the area here would be, let's say, because this is a rectangle that I have drawn, it is going to be nothing but acceleration into time, which is nothing but velocity. Now the reason why I'm telling is we found acceleration as velocity by time, or let's say more appropriately delta V by delta T will be equal to delta A. So similarly, I can find that delta V is equal to delta A into delta T. So the acceleration time graph is more useful to calculate the velocity of a given body, whereas the velocity time graph that is there helps us in determining both acceleration and the displacement that is there. If you go back to the displacement time graph, it helps in determining only the velocity. So we can write all of it like this in this particular way. So we can say that displacement time graph, the slope gives us velocity. Velocity time graph, the slope gives us acceleration and the area under the curve gives displacement. And the acceleration time graph gives velocity, which is area under the curve. Now what is the use of knowing these things? Now we have got three equations of motion which we write like this. V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. Now these graphs help us in determination. Specifically, if you look at the velocity time graph, it helps in deducing all these three equations that are there. So the knowledge of the graph is important for us to understand the motion of the particle. Secondly, from the velocity time graph, we can go ahead and derive this. So graphical way of deriving these three equations of motion, we will look at it now. So let us now look at how we can do this. So for this, we will take a simple graph that is there, which looks like this, something that we've already taken for the velocity time graph. Now, this is along the y-axis, we will have velocity in terms of meter per second. And on the x-axis, we will have time. Now, what we will do is, we can subdivide this into two different shapes, geometric shapes. One as a triangle, one as a rectangle that we did previously. So for this, what I will do is, I will use two different colors. So this forms my triangle here, and with the blue, I'm going to finish my rectangle that is there. So this is my rectangle. Triangle is complete. Now we can go ahead and label this as, let's say this is O, A, B, C and D. Now just for our ease, what we will write it is like this. So at point A we have U, which is nothing but our initial velocity, and at the rate point B it is going to be V, which is our final velocity. Now at O we have the time, that is 0 seconds, and at D we have time is equal to t seconds. So right now we have labeled all the parts that are there for this graph. Now let us go ahead and find out. Let's say for the first equation of motion we will take acceleration. Now, acceleration is nothing but the slope of the velocity time graph. So the slope, I can simply take it as, in this case, it is BC by AC. Now you can't simply write it as AB by BC every time. You have to look at how you have labeled the diagram that is there. In this case, BC is my the AB is the hypotenuse, BC is the opposite side, AC is the adjacent side. So this angle is theta, this is 90 degree. So tan theta is nothing but BC by AC. And BC can be written as V minus U. So this is V minus U, and let's say this is T minus 0. So AC and OD are similar. So therefore, and this is simply written as U. So BC is V minus U by AC is T minus 0. So we can go ahead and write it like this. So A is equal to V minus U by T, or AT is equal to V minus U. That implies V is equal to U plus AT. Now this is the first equation that is there. The second equation talks about displacement. So for that, let us have a look at this. So here displacement is given by the area of triangle ABC plus area of rectangle ACDO. Now this collectively can be written as area of quadrilateral OABD. Now since I've already drawn it in this particular fashion, I've just simply written as triangle and rectangle, the areas. But you can write it as area of the quadrilateral and apply that formula also. You will arrive at the same value. So let us have a look. So the area of the triangle, if I take, let's say, triangle ABC, is nothing but half, base is AC, height is BC. So I will get this as half into AC is T, BC is V minus U. And if I look at the rectangle that is there, ACDO, it is nothing but length into breadth. That is, we can write it as CD into OD. And CD is U, OD is T. So let us add. So the displacement is nothing but half T times V minus U plus UT. Now it is known that V is equal to U plus AT. We just derived this. So I can simply write this as V minus U is equal to AT. So we have the value of V minus U. And S was written as half of V minus U times T plus UT, or half AT into T plus UT. Therefore, S can be written as ut plus half a t square. Now this is the second equation of motion that is there. So the first equation was v is equal to u plus at. We have derived that. Now let us look at the third equation of motion, how we can derive it. So now for the third equation of motion, what we will do is we will still use the same expression for displacement. But in this case, we will use area of the trapezium. That is AB, let's say we'll include C also, CDO. So this entire area we are including. Now I will use the formula for area of the trapezium here, which is nothing but sum of the parallel sides plus, or let's say into, not plus, multiply it with the distance in between them. And this entire thing you divide it by 2. So if we try and apply this formula, we will have S is nothing but O plus dB into OD by 2. Now what is OA? It is U. dB is nothing but V, because see, it is V minus U plus V, which is going to be nothing but V, into OD is time T, this by 2. What I will do is I'll take 2 to the other side. So 2S is equal to U plus V into T. Now we don't have any formula for U plus V, but time from the first equation, that is V is equal to U plus AT, I can write time as nothing but V minus U by A. So we can go ahead and substitute this here, and we can write 2S is equal to U plus V into V minus U by A. Now V plus U or U plus V is one and the same. So 2SA is equal to V plus U into V minus U, which is nothing but V square minus U square, using the identity A plus B into A minus B is equal to A square minus B square. So our final equation is going to be V square is equal to U square plus 2AS. So we can talk about our three equations of motion, that is V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. Now we have derived all of these three using the velocity time graph that is given to us. Now we have a concept called as free fall. Now in free fall, what happens? An object is dropped and moves only under the presence of the gravitational pull of the earth or under the acceleration due to gravity. So in these cases, what happens is our equation will be slightly modified. So when we look at free fall, so in free fall, what happens? The object is at a height h, and the initial velocity is 0 because it is dropped from rest. So our equation of motion, that is V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS can now be written as V is equal to GT, because the acceleration is nothing but acceleration due to gravity. The displacement is nothing but the height that is given, which is nothing but half gt square because u is 0. And the last expression, v square, is nothing but 2gh. So this is how our equations reduce when we are looking at free fall. Now there is another way of arriving at our equations of motion, the actual equations of motion, using pure mathematics and no geometry, which is called as the method using calculus. Now in calculus, what happens is, let's say I give you a graph which looks like this. So this can be, let's say, our velocity time graph. Since we have derived the equations using that, we will go ahead and let's say draw this graph. Now here, let's say I have a curve which looks like this. And if I ask you to derive the velocity time graph, or let's say the three equations of motion from this type of a velocity time graph, it's going to be a little difficult. You'll tell, stop joking. But actually speaking, you can do it. Now, the method of calculus that is there, it involves breaking this curve into small strips. So that means what we will do is very, very thin strips we will cut. So we will get rectangular strips, but along with these rectangular strips, there is going to be a triangle that is attached with it. So we're going to strip it like this. Let's say coming here. Yes. So here you can see that there's a triangle. So a slope is there. But at the beginning of the curve, the slope is very, very small that is there. Now, the two methods called as differentiation and integration, what we are doing is, in case of differentiation, we are breaking it down. That means here what I'll do, if I have to calculate displacement, I will break down the area under this curve as very, very, very small rectangles. So I will have a rectangle and triangle that is there in this kind of a column. And then I will find the displacement individually for all of these geometric shapes and then put everything together. The other one, that is integration, I will actually do it in a different way. It is the reverse process of differentiation. So we can tell differentiation is the reverse of integration, or integration is the reverse of differentiation. It wouldn't make much difference because these are mathematical processes bound by mathematical laws that are there. So what do we do in integration? Differentiation, we broke it down. Integration, we will take the entire thing. So in order to understand this, we will go ahead and do a small mathematical problem. So before we get to that, let us look at how we can differentiate. Now the only two formulas that you would need to know here is this. So I will have d by dt of x power n is equal to n into the x power n minus 1. This is a differentiation. And integral, let's say if I have x power n here only, x to the power n dx, this is going to be x to the power n plus 1 by n plus 1. So we're just going to use these two formulas and do the integration and differentiation. Now this topic will be covered much more in detail in math, but we do require these expressions from time to time in some of the chapters that we are going to solve. So we will look at its understanding right now. Now, I have written x. X is the function that is there. For instance, you would have written y is equal to mx plus c when you were in school. So when you had to draw a straight line graph, this is your expression. What is the understanding? The variation in the value of x gives you your value of y. So that means x is a function of y. Exactly the same thing here. X is a function of t. Now, in differentiation, we are breaking it down. Integration, we are putting it together. So what we will do is, let us take a brief equation. So I'll give you one expression and we will go ahead and differentiate it, and then we will see what happens. Now I will call displacement, that is y is equal to, let's say, instead of x, I will take time. So 4t square plus 3t plus, or we'll take a cubic equation that makes it a little more interesting. 4 3 cube plus 3t square, 12t plus 6. Now a couple of things that you have to understand. Whenever we are differentiating, the numbers that are there or the constants that are there, we are not going to touch. So here if you see, I can do a small addition. This is t power 1 and this is t power 0. It is a well-known fact that anything to the power 0 is equal to 1. So that means I'm not altering the equation. I've just made some subtle changes. Now, velocity is given as rate of change of displacement, that is dy by dt. Now, how did we arrive at this d by dt? It is known in, let's say, it's a general tendency for human beings to have work done in the shortest possible time. So if we look at the other version of this, which we are familiar, it is nothing but delta y by delta t, that is change in displacement with time. Now the idea here is, if the change in displacement is much higher for a small value of time, we will get a greater velocity. That means effectively we are taking a steeper slope that is there. So in the VT graph, we are taking a graph which looks like this. So it has a steep slope. Now here we understand mathematically that if we apply a limiting condition, delta t tending to 0, that means it's becoming a smaller value but not exactly 0. This would convert this delta and all these operations into dy by dt. Now this is the understanding that is there. So let us take this equation forward and do the differentiation that is needed. Velocity is dy by dt. Now I will write it as 4 dt cube by dt plus 3 dt square by dt plus 12 dt to the power 1 by dt plus 6. Now t power 0 is, okay, we'll just write it, d by dt of t to the power 0. Now from the formula when we apply, we can simply write it like this. If it is, let's say, d by dt of t cubed. Now what is our formula? D by dt of t power n is nothing but n times t power n minus 1. So applying the same formula here, dt cubed, that means n is 3, you write it first, t to the power 3 minus 1, which is 3t square. Similarly, d by dt of t square, it becomes 2 t to the power 2 minus 1, which is nothing but 2t power 1. D by dt of t power 1, it is 1 t to the power 1 minus 1, which is 2t power 0, which is equal to t. So this is 1 into t to the power 0, which is equal to 1. And now we have d by dt, the last one, as t power 0. So it becomes 0 into the power 0 minus 1. So 0 into anything is 0. So therefore, we can write our expression velocity as dy by dt as 4 d by dt t cubed plus 3 d by dt t square plus 12 d by dt t power 1 plus 0. Now substitution, I will get 4 into 3t square plus 3 into 2t plus 12 into 1 plus 0. So our expression now will be 12 t square plus 6t plus 12. So what have I done? I have reduced the cubic equation down to a second order or a quadratic equation that is there. This was the third order equation, that is in terms of displacement y. I have reduced it to a second order or a quadratic equation. Now this is velocity. We can go ahead and do acceleration. Now what is acceleration? So I'll just simply write velocity here, which we got it as 12t square plus 6t plus 12. Again, for our benefit, this is t power 0, this is t power 1. Acceleration is rate of change of velocity. So I can simply write it as dv by dt. But v is equal to dy by dt. So that would imply acceleration is d by dt of dy by dt, which is nothing but d square y by dt square. That means we are differentiating the displacement 2 times in order to arrive at acceleration. So mathematically, this is what it means. So here we are not using any graph. We are just using a formula and we are doing it. So let us go ahead and find acceleration. So acceleration is dv by dt, which is nothing but d by dt. We need not write this as d square by dt square of y because already we have differentiated it once. So this is going to be 12 times d by dt of t square plus 6 times d by dt of t power 1 plus 12 times d by dt of t to the power 0. So let us go ahead and solve the d by dt's and then we will see. So d by dt of t square will be nothing but n is 2 t to the power 2 minus 1 of t power n is given as n times t to the power n minus 1. So this will give you 2t. D by dt of t power 1 is 1 into t to the power 1 minus 1, which is 2t power 0. It's not 2, it is 1t power 0, which is equal to 1. And d by dt of t to the power 0 is 0, t power 0 minus 1, which is equal to 0. Now, we will go ahead and substitute these values in our expression. So in this expression, when we write, we will get 12 into 2t plus 6 into t plus 12 into 0. So the equation that we will finally get here is acceleration is equal to 24t plus 6, this is t power 0, so plus 6 is what I'll get. So I can actually write the final expression like this. Acceleration is equal to 24t plus 6. So you can see when we are differentiating what we have done, we have reduced the power from 3 to 2 to 1. So we've made this a simple straight line equation from a quadratic equation. So if I call this process as differentiation, the reverse of it is called as integration. So we can always understand that integration and differentiation as two up and down processes. Now what is the use of doing this? So we'll go ahead and plot a graph. So for that what we will do is we need to prepare a table where we have got the time that is varying. So 0, 1, 2, 3 up to a given number. We will have the values of y, velocity and acceleration. So we can plot a graph of v versus t, that is, let's say distance versus time, velocity versus time, acceleration versus time, and see how this graph looks. So here I have a table which has the x-axis in terms of time, y-axis in terms of the displacement. This is the equation that we have. Again, another y-axis for velocity, and these are the values, and the final one, acceleration, and the values. So you can see that when time t is equal to 0, for y it is 6, for velocity it is 12, and for acceleration it is 6. So accordingly, I have used the formula and I have calculated these values. So first let us plot, let's say, displacement and time and see how the graph looks. So this is how our displacement time graph looks. So it's a smooth curve which is moving upwards. Now we will plot, let's say, velocity time and see how the graph looks. Okay, so you have another curve that is there compared to the first one. We'll not be able to make out much difference here, but still, again, this is a curve. And let us plot acceleration and time and see how the graph looks. Okay, looks like a straight line. Now, in order to understand what I'm trying to tell with these graphs, I will plot all of them in the same graph with respect to the x-axis, that is with respect to time. So when I plot all of them together, you can see that my value that is there, in this case, if I see the black dot is giving me the displacement curve that is there, the red one is giving me the velocity, and the triangle, the blue one, is giving me the acceleration. So you can see what happens when I'm differentiating the slope that is there, the tan of the angle, tan theta, is decreasing. So here in terms of y, you would have a very good slope. You can calculate velocity. When you are, let's say, plotting a velocity time graph and you try to find its slope, you will find acceleration. Acceleration time graph, there is no slope that is there. So using this one plot, we can see that when I'm differentiating, what is happening is from a third order or from a cubic equation reduces to a quadratic and then finally reduces to a simple equation of the first order. Integration would be reverse. You can start from the first order and reach up to the third order that is there.